Hello, my name is Dr. Adrian Green, and today I'm going to talk about leveraging high-throughput screening data, deep neural networks, and conditional adversarial networks to advance predictive toxicology. So why do we need predictive toxicology? Currently, 85,000 chemicals are registered with the Environmental Protection Agency, and approximately 4,500 have rigorous toxicology data, leaving 80,000 chemicals untested. To address this data gap, high-throughput screening and computational methods are vital. So how do we predict toxicity? So computational approaches to bridge this data gap have been developed utilizing chemical structure. The two most common being quantitative structure-activity relationships, or QSARs, and read-across. And then recently, machine learning advances such as deep neural networks and conditional generative adversarial networks show promise but have not been thoroughly explored. So as part of this study, we took zebrafish toxicity data generated by Robin Tanguay's group at Oregon State University on over 1,000 chemicals at a range of different concentrations, and they exposed fertilized zebrafish embryos from 6 hours post-fertilization through 5 days. And they collected a range of morphological and mortality endpoints, ranging from edema to facial malformations, etc. So what are deep neural networks and cGANs? So in our case, a deep neural network takes 3D chemical structure as input into the input layer and then propagates this through fully connected hidden layers. In this case, I'm just showing two. And as an output, we're producing a toxicity matrix. And so the darker shading represents higher toxicity. And so these endpoints could be things like edema, mortality, facial malformations, etc. And what we want the deep neural network to do is learn which features are necessary to produce the most accurate toxicity matrix that is identical to the empirical one. And then this will give us a good tool for generating toxicity of unknown chemicals. So in a similar manner, a cGAN takes the chemical information into a generator and then produces a toxicity matrix. The next step is that it's fed into a discriminator, which then tries to tell the difference between the empirical matrix and the fake matrix and says it's real or fake. And so as the generator gets better at telling the difference between the two, the generator has to get better to compete with the discriminator. And so the end, in an ideal situation, is a well-trained generator. So what we did is we did a 10-fold cross-validation using some machine learning methods that are industry standards, so things like support vector machines, multi-layer perceptron, and random forest, and compared it to our GAN and deep neural networks in a 10-fold cross-validation. The two primary metrics we use to compare how well our models are doing is Cohen's kappa statistic and the OROC, or area under the receiver operating characteristic curve. And that tells you how well you're doing on unbalanced data. And so of the 1,000 chemicals, only around 200 are actually active. So we do have an unbalanced data set. And so as the numbers get closer to 1, that means that they're perfectly able to predict active versus inactive. And if the kappa is close to 0, it's random. And if the OROC is close to 0.5, we also have random. So you can see the deep neural network did by far the best, then followed by the GAN, and then the other machine learning methods were barely above random chance. If we then go on to look at a test set that was held out, this is a test set that was done at least 7 years after the original experiment, and so we kept this one as the holdout. We can see that the traditional machine learning methods actually do improve, and we see the GAN has actually decreased its performance, but the deep neural network still does the best out of all of them. We then went on to combine all of the models with the deep neural network individually, and the one that added the most additional information was the GAN. And so we can see that by adding the GAN, we can eliminate, at least in this case, 2 chemicals that are no longer being classified as active by the combined model. So why do we need predictive toxicology? Our combined model is a good predictor of empirical toxicity, and the combined model utilizing 3D chemical structure information is a useful pre-screening tool for predicting toxic outcomes of the approximately 80,000 untested chemicals. So the next step would be to create a priority list and develop deep learning methodologies to evaluate mixtures, as well as empirically validate any of our findings. So with that, I'd like to thank the members of my lab and our postdoc mentor, David Reif, and I'm happy to take any questions, and thank you for your time.